Alrighty, Chemistry 30, here we go into the final podcast for week 5. Assuming, which I probably shouldn't, that you're listening to this before Thursday morning, don't forget, please, you have that opportunity on Thursday to come to the Google Meet to ask some questions, because I know this is kind of weird stuff and different. It is at 11 o'clock Thursday morning. Look for details in Google Classroom on Thursday. Now, the last thing we're going to focus on this week on alkanes is cycloalkanes. Now, cyclo means exactly what you would think it is. It talks about when we make rings. Now, in this case, the parent chain is going to be a ring of carbon atoms, and they're still single bonds, hence it's an alkane. That's important. Wait, I think I was using orange for that before, so let's go back to that. Ane, there we go. So single bonds, right? And the ring is still saturated, which means that, like I said, single bonds, and we have as many hydrogens as necessary in order to get every carbon to bond 4 times. Now, in terms of how this is actually named and how we do this, we end up taking our group in terms of the family that it's a part of as being our not just an ane, but also the cyclo. So you got to put both, okay? So that's the suffix part, but there's a cyclo there too. In terms of the root, that's still going to be the parent. So in terms of that, how many carbons are in the ring? Now this is a little bit different. It's not always the longest number of carbons in a row anymore. With cycloalkanes, it has to be the ones that are joined in a ring. That's going to be the parent group. That's going to be the root, no matter what. Even if it's only 3 carbons, that guaranteeably is the root. This is just for goofiness that I have down here. Look at this name. Woohoo! I just want to show you that what we're doing in organic chemistry right now is, like I said, tip of the iceberg, guys. It's just the simplest stuff. These get a lot more complicated. These are very familiar molecules, testosterone and estrogen, right? So female and male steroids, essentially. And they've got a lot of rings in there. Some are definitely more complicated and stuff we haven't talked about, and there's some different things in there. But look at that name, right? So as much as when you're looking at this, be like, this is too much, this is so hard. Take a breath, try to digest it, think about it a little more, and realize you are at the tip of an iceberg, truly, okay? All right, let's talk about naming these things. Now, when you name them, there's some super important rules that you have to follow. We always number, and numbering any sort of parent root chain is really important, but we always number them to get to the branches at the very beginning. That means if there's only a single branch coming off of a cyclic hydrocarbon, no exception, you put that single branch on carbon number 1. In fact, that's how we decide how to number them. Okay, now because you're guaranteed if there is only one branch that it's on carbon 1, you don't have to put the name in that situation. As soon as you get more than one branch, then once again, this is familiar, you have to list them in alphabetical order. Remember, we don't use di, tri, tetra for alphabetical. Instead, we use the meth, eth, prop, bute, etc. Okay, we also, same as before, are going to have to show the numbers to give a relative position on that ring. Now, this is slightly different. We didn't do this with the regular alkanes. You must always number the entire ring to give the lowest possible numbers as a total. You can imagine if you, with a cycloalkane, added all the numbers together, it has to be the lowest number, okay? That's kind of a little bit of a hint, and I'll show you what I mean as we keep going. Little bit of a difference too when we draw cycloalkanes. We actually combine line structural diagrams with condensed structural diagrams. The actual parent ring, the one that is cyclic, is always drawn as a line structural diagram. Any of the branches, on the other hand, are always drawn as condensed structural diagrams. So like I said, it's a combination of both. Now, just reading all those words gets kind of wonky. Let's put this into practice and it'll get easier. Okay, so just to clarify what I mean by line structures for the rings, we just use geometric shapes for these. if you have, at its most simplest, cyclopropane, right? There's the prop, so it's a 3-carbon ring. You would show it as a triangle. Cyclobutane with 4 carbons is a square. Pentane is a pentagon. Hexane is a hexagon. I didn't draw a heptagon here. Heptagons are hard to draw. But if we had cycloheptane, it would be a heptagon. Cyclooctane, of course, is an octagon. You get the idea, guys. Geometrical shapes. Those are the line structures for the actual rings. Alrighty, these are the examples that are in your notes. Let's go through them. Notice with this one, we have a single branch. That means, without a doubt, unexceptional, this is carbon 1. Has to be. Now, in terms of which way you go after that, well, let's play around. If this is carbon 1, carbon 2, 3, 4, 5, 6 versus, and I'll switch to green, still make this carbon 1, then I'll go this way, 2, 3, 4, 5, 6. It doesn't change the name in any way, shape, or form. If I use the red numbers or the green numbers, I still get the same name. So keep that in mind. Always play with the numbers, but recognize sometimes it doesn't matter. Okay, name this thing. Let's look at what we get. Now, there's 2 options for our temptations of how to do this. The first option really goes back to how you named alkanes. It's very tempting to call this thing 1, comma. Look at this. It's a 2-carbon branch. So I'm going to make that ethyl. And then this is new. We have to include the cyclo. There's 6 carbons coming off around in the chain, so hex and then ane. When you first glance at it, you're like, yeah, this is good. I've got this. Woohoo. Nope. Sorry. You don't need that 1 there. This is the only time you don't, because honestly, guys, it has to be on carbon 1. There's only 1 single branch. So it's there. So the correct name of this is just that. Okay? Ethyl cyclohexane. That ethyl is the prefix telling you the branch. The hex is telling you that there's 6 of them. And then in terms of the group that this is in, it's a cycloalkane. So ethyl cyclohexane. Dun, da, da, da. There's our first name. Okay, let's try one of 2 branches. Woo! Now we absolutely have to have numbers and use the numbers in the name, because otherwise we don't know where the next branch is. Now you've got a couple choices here again, and let's go through both of them. The first choice is that we make the methyl branch on carbon 1. So let's try that. 1, 2, 3, 4. Even if I went the other way, guys, right? If I went 1, 2, 3, 4, I end up with the same. So it doesn't matter what direction I go through here. Okay? Anyway, 1, 2, 3, 4. Now I'm on 5, 6. That's one possibility. Let's go in green with the other way. What if I make the ethyl group at carbon 1? 1, 2, 3, 4, 5, and 6. Uh-oh. Okay. Let's go through both names here to make sure this is clicking for you. I'm going to do the red first. If I do the red numbers, I end up with ethyl on carbon 4. I have to write ethyl first because alphabetically it's first. 4 dash ethyl dash for another number, 1 dash methyl. This is a cyclo. It has 6 carbons, hex, and they're all single bonded ane. Okay, that's with the red numbers. Now let's do it with the green numbers. Okay, green numbers, my ethyl group is on carbon 1. 1 dash ethyl dash, my methyl group is now on carbon 4 dash methyl cyclohexane. Which one's right? They're definitely different from each other. Remember what we talked about before. You have to alphabetically number these properly. With the red one, my first letter, E, is going with a later number. My later letter, M, is going with an earlier number. Nuh-uh, that's not happening. The red one's wrong. The red way of numbering is incorrect. It does not work. Our correct one is the green. Yay! 1 ethyl. keeps alphabetically E with the lower number 1, 4-methyl cyclohexane. There it is. Okay, let's check out this one. Ooh, now we've got 3 branches coming off. 2 methyl groups and an ethyl group. Well, this gets interesting. Okay, still keep in mind alphabetical. Let's play around with the 2 ways of numbering this again. First way is I'm going to start with my ethyl. I get 1. Now here's a question. Should I go 1, 2, 3, 4, 5, 6, 7? Whew, and then I put the next branch on 7? Or should I go the other direction? Remember, before we ended up on 7. This, and I go 1, 2, 3. Ooh. Oops, sorry. Apparently I can't count. Here we go. 1, 2, 3. This is way better, guys. You always still have to think about your numbering to keep the total numbers lower. 1 going to 7. Woo, 7's high. 1 going to 3. Ding, ding. Much, much better. So we're going to go this way. 1, 2, 3, 4, 5, 6, 7, 8. Ooh, this is a cyclooctane. Okay. What if we go a other way where we put those methyl groups on carbon 1? Same thing. I'm not going to go 1, 2, 3 all the way around because I'm going to end up with way higher numbers then. I'm going to keep my numbers low. So 1, 2, 3, 4, 5, 6, 7, 8. Which one is correct? Well, look at the green numbers. The green numbers put 1 with methyl and carbon 3 with ethyl. The red numbers put 1 with ethyl and put the 3 with the methyls. From an alphabetical perspective, this is what we want. Alphabetically, E comes before M, so it matches the number better. In other words, the green numbers here are wrong this time. Okay, so I'm going to erase them. Green ones didn't work. They're wrong. We're focused on the red numbers. Okay, let's do this thing. Focused on the red numbers. I always do it alphabetically, so I'm going to write the ethyl first. It's on carbon 1. 1 dash ethyl. Now we'll move on to carbon 3 with the methyl groups. Dash. There's 2 methyls. I have to write it twice. 3, 3. Separate with a dash because there's 2 methyls. We say di. Di, methyl. Don't forget this is a ring. We need the word cyclo. It is a ring of 8 carbons. Oct. They're all single bonded octane. Yes, there are 2 O's in there. That's okay. That's how it's done. 1 ethyl, 3, 3 dimethyl cyclooctane. Honestly, sometimes you'll see it written with a single O instead of the 2. That's okay. Either way. Alrighty. Here we go, guys. Last step is drawing. We've got 3 more examples with week 5. I know it's a lot to take in. Believe it or not, this is seriously pared down from what we would have done in class. All right, drawing the cyclic hydrocarbons. We start these things off by drawing your ring. Remember, we do a line structural diagram, that geometric shape. And then the branches, on the other hand, are going to be drawn as condensed structural diagrams. There's exceptions to this. Let's say in the homework, you're asked to do the whole thing as a line structural diagram. Well, then you can. I'll show you an example of that. Okay, check out this one. Methyl cyclopentane. Woo, key thing to notice. See that cyclo. Don't lose sight of it, guys. We know that it's a 5-carbon ring. That's the pent. And we're also told that there's a single branch coming off. Where is that branch? Guaranteed. Off carbon 1. So do the pentane first. And this is where you just draw the geometric structure of pentane. This stylus and drawing straight lines. I'll try one more time. We'll see if I can do it. Oh, look, there's these. What's that? Shapes? Shape tool? Yeah, let's draw a shape tool. I don't know if this is going to work. This is probably not the right time for me to do this. Shape, 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 shape. No, that is not the shape I was drawing. Let's try that one more time where I draw it more pretty. Okay, careful. Yeah! Okay, sorry, new discovery. Okay, there's my pentane. The methyl group, where do I want to put it? I don't know. I could put it there. I could put it here. I could put it here. You get the idea, guys. Where you choose to put that methyl group is up to you. But no matter where you put it, it is carbon 1. Okay? And that's done. Methyl cyclopentane. Pretty simple. Okay, what if we've got a couple more branches coming off? This one's a little bit more complicated. It is still a cycloalkane, so it's going to have a geometric shape. It is hexane this time, so it's a 6-carbon ring. And we've got a few branches coming off. We've got a propyl 3-carbon side chain on carbon 3, and we've got an ethyl 2-carbon side chain coming off of carbon 1. Start first with getting your line structural diagram for that hex, right? Cyclohexane. See if this will work again. Nope, it didn't work that time. Let's try again. I sure like this if I can get it to go. 1, 2, 3, 4, 5, 6. Sweet, there it is. Okay, there's my hexane. Now, honestly, draw the ethyl first because that's carbon 1. So wherever you draw it, you're just making it carbon 1. I'm going to make this one's carbon 1 here, okay? As a condensed structural diagram, it's CH2 and then CH3. Now, that means that carbon 3 has to count from that being carbon 1. Whether you go clockwise or counterclockwise, who cares? As long as we count it as carbon 3. So I'm going to go counterclockwise. So I'm going to say this is carbon 1. This is carbon 2. That's going to be my carbon 3. That means coming off then, I've got a ethyl group coming, a propyl group coming off of carbon 3. So I draw a line. There's my first carbon, CH2. Second carbon, CH3, oopsies, CH2 again, and my third carbon, CH3. There's the propyl group. There we go, 1 ethyl, 3 propyl, cyclohexane. If you drew this as a line structural diagram, it would look something like this. Your initial cyclohexane is exactly the same, but then we would draw that ethyl group going out like that, and we would draw the propyl group going out like this. There it is, okay? Ultimately, all you have to think about is that the ethyl has 2 carbons and the propyl has 3 carbons. This carbon here is part of the original cyclohexane. This carbon here, again, is part of the original cyclohexane. All right, one more example, guys, just to finish us off. Looks like a complicated one. Don't make these harder than they need to be. This is, at its heart, a cycloalkane, right? So I'm going to start with a ring-like structure. It is a 4-carbon cycloalkane, and then I have some branches. A methyl off of carbon 2 and an ethyl, a 2-carbon chain off of carbon 1. But let's draw that butyl first, okay? Butyl is 4, which means we are literally drawing a square, okay? From that square, decide where you want carbon 1. Doesn't matter. I'm going to make this carbon 1 up here. So the first carbon on there is a CH2. The next one is CH3. My carbon 2, and I'm going to go clockwise this time, is a methyl group, CH3. There it is, 1 ethyl, 2 methyl cyclobutane. Do not lose sight of how many hydrogens are on these other carbons. For example, this carbon is going to actually have, if you can imagine it, another carbon attached up here, another carbon here. So technically, it would have 2 hydrogens on it, right? Just to visualize this. Same with this carbon, would technically have 2 hydrogens. This one, on the other hand, would only have 1, because now it's bonded 3 times. Same with this carbon. It would have 1 more hydrogen on it, right? Eventually, when you get to the actual worksheet and assignment, you're going to have to be thinking about that. How many times does each carbon bond? 4 times always, no exception. Alrighty, guys, you can do the remainder of the assignment. Notice that they're kind of mishmashed, so pay attention to this. 2BC, 3B, 4E and F, and of number 5. Number 5 involves some number crunching again. It goes back to a combustion reaction, so you're going to have to use a balanced chemical reaction for the combustion of the hydrocarbon, and then you're going to have to use stoichiometry to compare amounts. Have any questions? Let me know. Have a good week, guys.